All of the graph examples that we've seen so far are unweighted graphs. It's also possible for a graph to be weighted. So, what is a weighted graph? A weighted graph has a weight or a number associated with every edge in the graph. Now, these weights are generally positive, but it's also okay for these weights to be negative. The weight associated with each edge represents some kind of value associated with that relationship. Let's go back to looking at the simplest possible graph. We have two nodes here connected using a directed edge, and this edge has a weight of 2. The number representing the weight is generally placed close to the edge. The vertices in a graph represent entities, and the edges are used to model relationships. This is something that we have studied earlier. The weights associated with each relationship represent additional information that we have about that relationship. For example, if we were to consider A and B to be two locations on a map, then the edge connecting A to B would be a way to get from the source to the destination. Now, the weight associated with the edge could represent traffic conditions, the time taken to go from A to B, or the weight could represent the distance from A to B. When you specify a weight with every edge in a graph, that is a weighted graph. This is an example of a weighted graph. Observe that every edge is associated with a number. Now that we've understood how graphs are useful and how they work, let's talk about what is it that you need to represent a graph in a programming language. The first thing is you need a way to model a vertex, and this vertex might hold some information. It should have a way to contain some data. In your graph representation, you also need a way to model edges, either directed edges or undirected edges. There are three common representations of a graph. The first of these is the adjacency matrix representation, where the vertices in your graph form the rows and columns of the matrix. The second is the adjacency list representation, where you model every vertex and specify what vertices are adjacent to each vertex. And the last representation is the adjacency set representation. Here, for each vertex, you model the adjacent vertices using a set rather than a list.